So I'm Robbie McKinstry. I'm a recent grad from Pitt. Right now I'm interning at a company called HashiCorp. We build tools, but not these kinds of tools. So we build DevOps tools. We don't do anything with static analysis. I just like it. So we're going to jump right in. The talk is going to be structured as follows. It's going to be talked kind of what is static analysis in general. Then we're going to spend some time on how do you do it? How is it done in general? How do the tools work? And that's where the theory comes in. I'm going to do about 3 demos, and then we're going to talk about how you can implement it in the workplace. So as Steve mentioned, this is going to be a little bit more technical. When I said I wanted to give a talk, Steve said, that's great, let's meet up and talk about it. And we sat down in coffee tree roasters, and he told me my original idea was pretty bad, right? And my interpretation of that was that he was entirely correct, and that I totally did need to restructure the talk. So originally it was pretty theory heavy. Now it's pretty theory light, but we still have this middle section in here on how static analysis works, which maybe you'll humor me a little bit, and we'll talk a little bit about the theory. But I kind of pivoted the talk from its original idea pretty significantly, and I think it's significantly better as a result. Maybe it's still bad, but it's at least better than what it would have been. Okay, so does anyone here raise your hand if you think you know what static analysis is? Now raise your hand if your company uses static analysis tools in the workplace. Cool, okay, roughly the same number of people. So static analysis, very, very broadly, is a static analysis tool is something that takes as input in a program and then tries to determine properties of that program without actually running it. Static analysis is in contrast to dynamic analysis, which I imagine Pittsburgh QA probably spends a lot more time talking about, because dynamic analysis is testing, right? When you run your code, you're testing. And that is dynamic because the code is actually being executed. So static analysis involves no execution of running code. It typically is a particular program that takes as input a program and then outputs a set of properties. The canonical example of this is Turing's halting problem. The halting problem is what I think is maybe the first static analysis program discussed. The idea was that Turing was trying to address the question of, can I write an algorithm that will look at a program and determine whether or not it will loop infinitely? Or will I always be able to know whether or not it's going to loop infinitely? And the conclusion is, sometimes you can look at a program and say, yeah, it will definitely loop infinitely. Sometimes you'll look at a program and say, no, it definitely terminates. But you can't always tell. And I think Turing's solution was probably the first example of static analysis, and that one that you might have heard of in the past if you were somewhat familiar with history of computer science. But we're particularly going to be talking about how people can use static analysis to look at properties that are actually meaningful for their code. So the next question we're going to ask is, what are the properties that you can actually discern with static analysis, and what problems can it solve? So here's just a non-exhaustive list of some of the problems that static analysis can solve or can be useful for solving. And the most obvious one that sticks out is type checking, is that any instance of type checking in your program is actually a form of static analysis. When you run Java, when you compile Java code or C++ code, you're trying to make some guarantees about the kinds of memory so that you don't end up in a situation where you're multiplying Booleans by strings, right? Type checking, type annotations allows you to make sure that you don't have those classes of errors. And of course, the opposite of this is something like Python, where it's just the Wild West, and you can multiply Booleans by strings and things like that, right? Another instance would be SQL injection. I'm not going to go through the whole list one by one, but SQL injection, a static analysis tool will look at user input, and it will make sure that it gets cleaned before it gets run in your database, right? Before you actually execute it as database code. Other really interesting ones, just to point out, are static analysis can check race conditions, and it can also look for array out of bounds errors and smashing the stack, and other kinds of non-trivial to predict security issues. Okay, so now we're going to get into a little bit about how it works. The idea in general is that you don't really want to track the entire program state. If you track every single instance of the program state, you're pretty much running the program, right? So what you do is you abstract over the program state and only focus on the things that you're interested in. So in the case of SQL injection, you only want to track, okay, hey, this string is user input. Is it clean or is it dirty? And that's actually why I have in parentheses here. It's called a taint analysis, actually. You want to see, is this possibly tainted? And you want to make sure it's not tainted before you actually inject it or run it as a shell command or whatever crazy stuff you're doing. You only track the things that you're interested in, and the amount of detail in how you track determines the precision of your analysis. If you've got really low detail and you're only tracking something very simple, your analysis is going to be very imprecise. And as an example of an imprecise analysis, we're going to talk about sign analysis. So sign analysis is kind of like the hello world of static analysis. What you're looking to do is you're looking to look at any integer, and you want to check to make sure if it's positive, negative, 0, or unknown, what its sign is. And the reason you might want to do that, some of the applications are for making sure that you don't index into an array with a negative number, because that would be an error, right? That would be an array out of bounds. Or you want to make sure that you don't divide by 0 and other kinds of things like this. Steve?
Why is it bad to divide by 0?
That would, of course, be an exception and probably a defect. I imagine in most cases when you divide by 0 and you throw exceptions, you probably aren't looking to do that. So sign analysis is a way of preventing defects, and thus that's why we're here at Pittsburgh QA talking about how to prevent defects. So here are just the first 4 rules of sign analysis. Bear with me a little bit. I've got an example on the next slide. The idea is that if I have an integer x, okay, and I'm storing a value in it, if it's a constant, I already know what sign it is. If I'm storing x equals 5, I already know it's positive. If I'm storing x equals negative 10, I already know the sign is negative. But when you start doing arithmetic on values and saying, a is equal to b plus c, this is how the sign flows through the program. So you're only storing the sign here, and you're only storing, if you've got 2 positive numbers being added together, the result is going to be a positive number. If you've got a negative number minus a positive number, then the result is still going to be negative. Anything plus or minus 0 keeps its sign. So I'll show you an example of what a sign analysis would do as it walks through the program. Right here, we've got just a couple lines of Java code or C++ or whatever you want. We start off just by setting x equal to 5, which means that our analysis maps the variable x to the abstract representation of its sign plus. At this point, the program does not store the actual value 5. It doesn't know that x is equal to 5. Our analysis only knows that x is plus, right? This is a very, very weak abstraction. Next line, we add y. We add y to the scope, and as a result, our analysis keeps track of both x and y's sign. We know that y sign is 0 and x's sign is positive. But then when we come down here, we end up resetting the value of x to be x plus y, and we follow. This is an application of our rule down here. Positive plus a 0 is a positive. As a result, x's sign remains the same. It is still positive. Does that make sense at all? I mean, it's a kind of abstract example. Phil?
What does that tie into integer overflow?
So integer overflow is usually it's like the fringe problem, because every language handles integer overflow differently. Some languages throw exceptions. Some languages just let you overflow. So in sign analysis, you don't really work with integer that's usually undefined behavior, right? Assuming that's kind of its own analysis on its own. Is it possible for me to overflow an integer? Yeah, I mean that's like its own kind of question. Steve?
What's integer overflow?
Oh, integer overflow is when you have you've got like 8 bits allocated for a number, and you add you overflow the number of the available space in that 8 bits. So you have 5 million instead of it only holds 256. Does that make sense? Does everyone follow with integer overflow? Okay. Cool. However, so with sign analysis, this is where we get into some of the weaknesses. What happens if you have an arbitrary positive number plus an arbitrary negative number? Can you know the sign afterwards? Probably not, right? If it's arbitrary, there's no way to know the sign. Similarly, a negative number plus a positive number, because addition's commutative, you can't know the sign afterwards either. So you lose some information when you only track the sign. If you're only ever tracking the sign of a number, if you have a positive plus a negative, you can't know what the result is. Now, the motivation for why we're not actually tracking the full number was, that's kind of like full program execution. We'll talk about that a little bit later. Sorry, I'm getting off track a little bit. But as a result, this analysis can be a little bit weak, and we can actually have unknown values in our program. Here's an example. If we have x is equal to -5, the analysis tracks the negative number. If we have y is equal to 6, the analysis tracks the negative number on x and the positive sign on y. But then when we add them together, since it doesn't know, it's not storing that x is 5 and y is 6, all it sees is a negative plus a positive, and it can't know whether or not that result is going to be a positive or a negative number. As a result, we now have x is equal to unknown, and now we don't really know the state of x, and our analysis becomes less useful because we're not actually able to check whether or not there's a divide by zero error, whether or not there's an array out of bounds error, so on and so forth.
So the x will be unknown in the most cases anyway, because the way you're presenting x as integers, it's not going to be the real case scenario, because those data is going to become somewhere outside. When you run your program, you won't be hard coding x is equal to 5 or x is equal to 50.
Yes.
Most probably that will be coming from somewhere in the data by the time program runs. Static analysis is before we run the program. So this will be unknown in most cases.
Yes,
what I'm saying.
absolutely. So I'm actually about to get to that. So the next claim is like, okay, well, obviously the sign analysis is weak because we end up with an unknown value. Can we do better by actually tracking the constant values? If we do a constant analysis instead of a sign analysis, we actually track the constant values. And then we can actually determine, okay, 5, whatever it is, -5 plus 6 is still going to be a positive number, right? The reason why this isn't full program execution is because at the time we're still ignoring strings, we're not allocating memory in arrays, we're not allocating objects, things like that. We're only tracking constant values. And so you end up with a much lower memory overhead than if you had run the full program. However, constant analysis still has some problems, as we pointed out. Most of our data does not come from hard-coded values, right? Oftentimes we end up with reading in from standard in, or if you're doing a CLI, or reading in from HTTP requests. Most of our values are unknown at runtime. And as a result, you end up propagating even more question marks. So this is part of the problem of static analysis, is that if a lot of the data is known at runtime, you end up with a bunch of challenges about how can we actually determine some of these properties. There are a lot of solutions like symbolic execution, which can solve these problems. Maybe we'll get to that. Maybe we'll have time. I kind of find it unlikely. But maybe I'll talk about that at the end. But there are some certain significant problems with static analysis. For example, this. Skip this slide. Okay, so why, if static analysis is so bad, why can't we just use like dynamic analysis? Why even use it? Well, when you actually run the code and you actually do tests are very limited. The reasons that they're limited is that you have intermittent failures. You can't test all edge cases in your program because as your program configuration grows, the number of edge cases grows exponentially. Sometimes race conditions only appear under certain scenarios, and I'm sure everyone here, if you're involved in QA, probably has some weird story about how you found this bug that only occurs when someone enters Arabic text. Works with Chinese but not Arabic, right? So everyone probably has some of these issues, right, that they've experienced in the past that the tests don't catch. Tests can't catch all errors. Steve?
That was good timing.
Steve?
Why can't we just run the complete combinatorial expansion of all possible program inputs?
That would probably work. You could probably successfully determine whether or not there are any bugs, but your program will not run before the heat death of the universe. So if you test every single integer in existence, right, you do 1, then you do 2, then you do 3, and you run those tests, you're never going to finish your programs. So that's actually part of the power of static analysis, is that if static analysis does find a bug, then you can actually prove, it will prove that the bug does exist, right? It will prove that, hey, I found this bug, and if you run it with this particular input, if you run your program with this particular input, you can reproduce it perfectly. Unit tests are either red or green, right? They either pass or they don't pass, and you have to add a new test every time that you want to try a different combination. Furthermore, as a result, there are diminishing returns to the kinds of tests that you can run. So if I have a function and I write 3 unit tests, I might say, okay, that's pretty decent coverage. Like, I'm pretty certain about that. I won't be as certain about it as if I had run 10 unit tests. If I had written 10 unit tests, I could say I am more confident about the correctness of this function. My confidence grows a lot. But then when I go from 10 unit tests to 50 unit tests, my confidence grows and I can say, yeah, this is a really well-tested function, but it's not growing as much, right? Your confidence has a diminishing return. You're doing more work for less confidence. 100 unit tests, similarly, is not, it's like, what's the difference between 100 unit tests wrapping a single function and 50 unit tests wrapping a single function? So they're both useless, right? And one probably is going to get you fired for spending too much time writing a set of unit tests. But if static analysis can find the bug, then you can know for certain that the bug does exist, and you can reproduce it. So now we're going to do a couple demos. I think I'm doing pretty well on time. So we're going to do a couple demos. The demos start with really, really simple stuff, and then they move into a little bit more complex stuff. The really interesting stuff where you're only analyzing abstract values, we're not going to get the time for the demo that, but I can talk about it and pull up some links. And I didn't make a link slide, so I'll put the slides in the meetup group, and I'll also put a list of all the tools I'm using and links to them. I'll do that on Friday. Okay, so the first one we're going to do is Golang, the language. Anyone who here is familiar with Go? Okay, so Go is a programming language developed by Google, and I like it. It's my language of choice, but I like it particularly because it's really excellent tooling. So I'm going to go through an example of auto formatting, which is a really, really simple static analysis tool for maintaining style. This isn't a correctness one. This is actually a style one. I would imagine you could make an argument suggesting that style is some derivative of correctness, where if you have that guy on your team who likes to have his if statements without braces, you've probably been bitten by the bug, right? Where it only follows the next, you think that there's a brace because it's indented. Style needs to be consistent in order to prevent user error, right? Human error in the developer. Okay, let's switch over. Can everyone see? You can't see my directories. That's not really important. But is the yellow text good?
Yeah.
Cool. Okay, so let's see. Okay, I've got a small Go program, and this is miserably formatted. So I've got a block of variable declarations, and they're all misaligned. My for statement has a brace. It ends the brace on the line here instead of dropping down. It's not pretty code. In Java, you might have formatting where your for statement might not have a brace, right? That leads to its own errors. But Go comes with a built-in formatter. So all I have to do is run go funct main.go, and it will reprint the file with mapping tabs to spaces or spaces to tabs as you see fit, and aligning everything and fixing our small errors. Does that make sense to everyone? Why you might want to do that? Okay, and then of course you can, output this, this prints the standard out. You can just write it to a file or overwrite.
Can you put the text before and after side by side? It'd be easier to compare the two.
Yeah. Oops, wrong directory.
Alright, before on the right and after on the left.
The other way around. Before on the right, before on the right, after on the left. So there's a little bit of the difference, right? It just realigns all the code and then moves the brace. This is a trivial example, but It's really useful for when you hook into your editor, so that every time you save a file, it automatically reformats your code. The other benefit to this is that it means that there are no style wars among your different communities in your organization. And the third aspect that a lot of people overlook is it's really, really easy to vendor dependencies from the open, pull in these open source dependencies, and then immediately be able to contribute back and understand the code and see, okay, this code is styled well. Okay, I already can grok the code because, for example, it all looks the same, right? There's never a case in which someone ends up, misformatting their stuff and it's just horribly styled because everyone's using the same style guide across the entire Go ecosystem. Okay, so that's just auto formatting, right? So this is a super simple one. The way this works is it just picks up the file, parses it, and then drops it back down, right? Cleans it up as it drops it back down. It just prints out what it expects the file to look like. So it's totally idempotent. You can, if you run the Go formatter over and over again, it's always going to produce the same results. So next we have a linting example. Who here has used linters? Okay, so a linter is actually a kind of static analysis tool. Linting just looks for style errors and well-known human errors, and then we'll try and correct you on those, right? So here we have a similar Go file. This one is actually the version as before, but formatted. And then the only difference is in this one, I have the same variables declared. I put them into an array, and then I loop over the array. When I'm printing out the words, I don't know if anyone can see this. I'm using print line. Now this is like a little bit Go specific, but it readily applies to Java or C. If you use print line, you're not expected to format string, right? That's what printf does, right? So printf expects a format string. Print line is just variadic and will take the first string and then print the second string and then print the third string. So this is actually an instance in which this is a kind of pretty subtle, in which I'm expecting a format string. I'm using a format string, but that's not what this function is supposed to do. I've got my print line confused with my printf. So actually, we might see. No, okay. If I actually save this file, I have built into my editor the Go linter. So it will warn me and say, hey, look, there's actually a problem here. But I'm going to run the linter from the command line. So what is it? Go tool vet. And here it will warn you, hey, look, you have a formatting directive and a print line call. You should be using a printf call. So that's like a subtle detail that might or might not be caught. It's probably more user experience. Yes?
Is there a way to suppress that warning if you decide that it's inaccurate?
Yes. You can suppress warnings. I think you can toggle on which ones you want. And then you can also suppress or toggle whether or not this returns an error code. So for CI, you might say, hey, I want you to run the linter, but I don't want you to fail and fail my build as a result. Or you could say, please fail my build if there's an error like this. But Go vet, for example, this is built-in tooling into the Go command line tool. It also watches for shadowed variables, and you can even do race detection in the Go tooling is built in. So those are just two examples from Go. What time is it? Okay, I'm doing okay on time. And then we've got one more example in Java. So let's see. Let's open up main.java. Okay, so this one's a little bit longer. This is two different errors. So this is a Dataflow tool. So the way Dataflow works is very similar to sign analysis and constant analysis. When I was describing those things, I was really describing Dataflow tools. They walk over the lines one at a time and then store an abstract representation of the program and then looks for errors. So in this one, these are more kind of subtle bugs, but bugs nonetheless. This is an example in which I'm using string.replace to change Timmy to Tommy. Okay. Now this might not be. Does anyone know what the problem is in this one? why this line does not update the word name to Tommy from Timmy?
Because they're immutable.
Because strings are immutable in Java, yeah. So this is kind of more subtle, and I actually was bitten by this bug in Python before, the pending to lists and things like that, because the pending to lists is mutable in Python, and I thought it was immutable. So I've actually been bitten by this kind of stuff before. Whoops. But this is an example in which we say, okay, if name has been changed to Tommy, then we said, okay, we successfully replaced it, and if we didn't, we just say, oh, it didn't work. What you should be doing here is you should be saying name equals, right? And that would be the correct way to write the code, but it's really easy to forget that replace has a return value. In the second one, we have a map. Now this is actually, you can just find this bug by looking at it, but if you assume that map was injected as a parameter, it's a little less obvious. So you've got a hash map. We set string x equal to mapper.get foo. Now, since we know that this mapper does not have the key foo. I never set the key foo. What is mapper.get going to return? It's going to return null, right? Some languages might throw an exception, for example. But in Java, this is going to return null, and now we're going to set x equal null. And when we call x equals x.replace, we skip over this line because x is null, and this is going to null pointer error. Everyone with me? Cool. As a result, what we'd like to be able to do is we'd like to be able to have a tool that knows, oh, this is possible that mapper.get could return null, and checks every single path to make sure that before I use x, it has thus been set to something not null. So if I had an else statement here that captured it and updated x with some string and made sure that every single path of execution was not null, that would be kind of ideal. So I'm using a tool called FindBugs, which was originally developed as an academic project, Java FindBugs. It was originally developed as an academic project, but Google picked up the authors of the tool and had them internally as part of their QA process incorporate FindBugs into the Java check-in at Google. And then they wrote a really killer paper on how they did that and how successful that was. And it turns out FindBugs is actually really great and really powerful at suppressing warnings. But this is an example of Dataflow. Let's see, okay. So the command I'm running is, I have the FindBugs jar right here. I'm running it with a text UI. It comes with a GUI, and then I'm running it over the package jar from this main file. And you can see, after a little while, it prints out a bunch of different errors. It actually catches a bunch of errors here, more than I actually spoke about. So it catches possible null pointer dereference, which is exactly what I spoke about. It catches the string.replace. Okay, so let's see. I guess I'll do it on my. Oops. Here we go. Okay, so here it catches the null pointer error. Here it catches the string.replace error. And then it says, hey, this has no side effects. It looks like it's useless. It's not returning anything and has no side effects. So that's a pretty interesting problem. It's like dead code. Dead code detection is another kind of static analysis. And then actually here we have a dead store in L1, right? So this is running over the bytecode. So L1 is probably a register or something. But the reason is that I set x equal to x.replace, but then I don't do anything with the return value. I don't do anything with this new value of x. So I'm storing this in memory, but I'm not using it. And so we actually find a bunch of bugs here. We found more bugs than we were expecting to find, right? So FindBugs is a really powerful tool for logic errors that kind of go beyond style, go beyond simple pattern matching, things like that. It actually can flow through the program and do the more powerful things well beyond the sign analysis. They can actually do these things like null pointer detection across every single path. So that is, those are the demos. So we did the Go Auto Formatter. I'll go back to present mode. Switch over So we did the Go formatter, we did the Go linter. Just in case let's say not everyone works in Go. I pity you. But these are, linters exist for every language. These are a couple of the other big ones. So check style for Java is really, really great. It's really great for integrating into your Ant builds. And it's super configurable, and there's like 120 different checks. It's a really powerful tool. I've never used RubyLint. The Rust community loves Clippy. Pylint and JSLint are well known for being like super easy to set up, really configurable and really powerful tools. Kind of like de facto standards of like you kind of should be like, at least in JavaScript you should be using this, especially because JavaScript has so many gotchas. But for whatever language you're working, whatever ecosystem, there's probably a tool for that. Then we just did the data flow analysis one. And then lastly, the last thing we're going to talk about is when do you use static analysis tools? Because a lot of us here are practitioners. We kind of want to know at what point in our workflow do we end up employing these tools? And so the first answer is kind of the lazy answer, right? And I mean that in like the lazy evaluation sense. The lazy answer is you just use them in CI, right? So in CI, you just plug in these tools, and it means that no one has to install them.
What is CI?
CI is continuous integration. A CI server is a server that sits separate from your source control repository, so that when you check in your source code, it will pull down your source code and run set of tests, or static analysis tools, or generate build artifacts, things like that. Does everyone understand? Does everyone get what CI is? Okay, cool. So lazy approach would be to do it in CI, in which like not everyone on the team has to have the linter installed, but during the CI build process, you can at least check, hey, am I growing a huge list of errors? Am I growing a huge list of lint violations? Is somebody checking in new code that is potentially dangerous? The next step, if like you really want to be a little bit more principled about it, is to download and install as part of your development environment these tools, and then hook it in so that when you run your tests in development, at that point you also run your linters and your static analysis tools to make sure that there are no new bugs. This catches the bugs before they go into CI and before they go into the staging environment, and it kind of puts the onus on the developer in order to be a little bit more careful about what they're checking in. And then finally, kind of like the next level of anal retentive about static analysis tools, just where I am at, if you couldn't tell, is in your code editor. So at least with Vim and assumedly Emacs, for a lot of these tools, they have built-in integration into your editor, so that on save you can then run the tools. And so this is really great for developing in, let's say, Go or Rust or Pylint, because it means that you are never looking at bad code. When you can write as much bad code as you want, but as soon as you save your file, it gets auto-formatted. And then it looks like everyone else's code, and then everything's hunky-dory. Yeah, that's kind of like the most extreme. That's kind of the conclusion of the talk. If we do want, I think we can hallway track or talk a little bit later about symbolic execution, which handles arbitrary data that gets read in. I think we'll hallway track that one. But that's kind of the summary. Once again, my name's Robbie McKinstry. I'm currently a researcher at HashiCorp. My internship ends in November, so I'll be available for a job. Any questions?
So in the previous slide that you mentioned, we also mean during the code review?
Yeah.
When you send for the code review, and then
right.
like people.
So there are a number of tools that will run in CI, right? So they'll run when you check in the code, and then they'll comment back to GitHub or whatever your code review, maybe Garrett if you're using Garrett, your code review interface of choice, and say, oh hey, on line 5 there's a lint violation, or on line 10 here's a possible null pointer error. So an example of that would be Hound for Ruby, and there's also for HTML and CSS, just some really powerful tooling that says at the CI level, we're then going to then apply this and pass the information discovered at the CI level back into the code review. Does that make sense? Any other questions?
Yeah, so where would you implement the static analysis tool if you are in the other, let's say, 70% of software companies that because of one reason or another are not CI, don't do that, they don't have a lot of unit test coverage, and you just have a bunch of manual testers that know a little bit of scripting, and you run into situations where there's a feature and the feature has been put in, and you can have essentially complete coverage of that particular feature. Like if you're in Java and an enum or something like that you can't potentially completely cover by static analysis. Where would you recommend implementing the static analysis in that case?
Yeah, okay, so that's a great question. It starts at the process level. It starts in the management level, in which maybe QA collectively or maybe an individual can really push for it. But the idea is that you need a group of people to decide, hey, we want to do this, right? And maybe in the past we have this huge legacy code base that's totally uncovered in tests, but static analysis might be a good way to get started even before the unit tests, right? At least let's make our code clean, guys, right? So it comes at the human level, in which you need to get everyone together and kind of agree, hey, we're going to start to move in this direction, okay? So once you get buy-in either from the devs or from the QA team kind of suggesting it or demanding it, at that point you can kind of incrementally add static analysis tools into your workflow. So you've got 50 nested directories. Let's just start at the leaf level, and we're going to run tools only over the leaf level. And most of these tools are configurable to do that. I know, so the Go tools all are, the Rust tools all are, and I know I've personally had a huge code base of Java code. I was working on a compiler at CMU, and the researchers don't care about style at all, right? So I was incrementally adding check style to subdirectories, and I put it in this case I put it in CI and said, hey, make sure that I've cleaned up this directory. Make sure that before you check in the code, there's no violation. Otherwise, your build will fail. But it comes down to having individuals push for principal development. And so you'll clean out a single directory, and then in your local tests or your local build process, whatever your build process is, you're going to violate if someone goes back in and makes it ugly again. Does that make sense? Does that answer your question?
Yeah.
Okay. I want to make sure I'm answering your question.
So if I may,
Sorry.
I just wanted to add, someone on YouTube pointed out Koala. It's language agnostic linter command line linking tool.
That's cool.
That's relevant right now.
Koala with a C. Phil?
one other thing you might try is divide up the tests, the static analysis tools into fast tools and slow tools, and have a util script directory or whatever which can invoke all the fast ones, and then gradually push, and another tool to invoke all the slow ones, and then gradually push people to use a pre-commit hook in Git, so that when they try and commit their changes, as long as the result comes back in less than 2 seconds, say, then it's not too much of a drag, and you can get people into the flow of it. And then people will say, why do I have to keep running this? Or what can we do about that one person who's still refusing to do this? And at that point, you can start looking at what are your options for your centralized source code server to be handling this automatically for everyone, much in the way that GitHub or any of the other services do.
It's a good point. And the other thing is that is something to note, is that some of these tools can be slow. Linters are super fast, auto formatters are super fast, but the Dataflow tools can actually take a significant amount of time to run. I actually had a professor who was doing automatic bug fixing, so they would identify where bugs were and then generate code to patch. It was patch generation. And the idea was that, hey, I can just grab a bunch of source code, run these tools, and then claim bug bounties. And so she literally wrote like a distributed system on AWS infrastructure and then measured like the amount of money she would have claimed for the bug bounties versus the amount of money that it costs to run on AWS. And so she showed that like you can find a bunch of different bugs for like under $7 or something, right? So something like she found like 100 bugs and was able to automatically patch 50 of them with just code auto patching, patched 50 of them. So this is Claire West wrote this, and it's called GenProg, and it was in Papers We Love. If anyone's familiar with the conference, she spoke at the Papers We Love conference on this solution. Steve, you had a...
Yeah, you actually sort of anticipated my question, but other than that particular instance, in the ecosystem of static analysis tools, what are you seeing in terms of their ability to recommend fixes?
So that's actually really interesting. So again, this gets into symbolic execution. You can, so we'll go back to this example real quick. I'll just give a real short discussion of symbolic execution. When you get to this line, y is equal to the next standard in, you can write a tool that says, okay, I'm going to assume the user is going to put in anything. Okay, it's anything from negative max int to positive max int, and then as I go through my code, I'm going to be tracking. Okay, now x is equal to whatever it was plus something in the range negative max int to positive max int. Then, avoiding any of the theory behind this, you can actually run a theorem prover to find the specific values that will cause errors. So I'll give you an example of some source code for that problem. So here, okay, thanks. Good catch. Here on the left is some C code. This is some C code I was writing. I was really trying to get a better example of symbolic execution in, but I didn't have the time. We bring in a value from command line arg, and then we transform it with some math equation, and then we divide. The result is 100 divided by y, right? And so an astute, if you're really quick, you might see that this is actually a quadratic formula. Okay. So there are some places in which y is going to equal 0. There's some numbers that exist in which y is going to equal 0. And if the user from the command line enters in those numbers, then you're going to divide by 0 here. So a symbolic executor can actually it will solve the quadratic equation and then find that, hey, you can, if the person enters in 4 and you run this program with the input of 4, you're going to crash because you've got 100 divided by 0. And the tool, I'm going to pull it up real quick. The tool I was looking at using, and this is like a really, really good one for C, if you do C development, it's called CLE. This kind of really sets a stage for symbolic execution. And CLE, for example, will find this error. I couldn't get it working, but I didn't, my own idiocy. But CLE will, for example, solve this quadratic equation and say, hey, if you put in 4, you can reproduce this error, right? And it will give you concrete input into your program that will cause a bug. CLE ran over core utils in Linux and found something like 60 reproducible bugs in core utils in Linux. And for each of them, it said, hey, there's a bug, and I'm going to give you the input that says run this, just add like ls and then this junk, input, and it will error out. So that is kind of in the wild what people have been using static analysis for in really powerful ways. What's the phrase, Justin? You gotta know this phrase. It's like any bug is shallow with a million eyes or something like that. It's like the idea is that.
All bugs are shallow.
Sorry?
Given enough eyes, all bugs are shallow.
Given enough eyes, all bugs are shallow is kind of the open source motto of if I open source OpenSSL and I have 1 million people able to look at it, every bug is going to be super easy to find.
Is the recent corollary where someone basically pointed out what actually happens is given enough bugs, all eyes are shallow.
Yeah, good point. And I think it was Heartbleed or Shell Shock kind of proved that this is kind of a false idea. That given enough eyes, not all bugs are shallow, and so sometimes you need static analysis tools in order to find them. Okay, so that is the presentation. Any other questions? Namaste.
Thank you very much.
All right.